Uh, Good morning or good afternoon, everybody. Now, after 1 minute, we will start the next invited speaker. If anyone has a question, he can write it in a chat or waiting for by the end of presentation and they give us his or her question. It is our pleasure to introduce our invited speaker, Professor Fary Z, who is going to talk to us about organic LED-based visible light communication. The talk will cover the recent research and development in the field of organic LED, which is being carried out with the Optical Communications Research Group or Northumbria University, Newcastle, UK. Professor Fary is the head of this research group. He is IEEE and OSA fellow. He also is senior member IEEE. Professor Fary has an over 860 published paper, and he is invited and note speaker for more than 100 talk, and he is supervised about 65 PhD students. Welcome, Dr. Fary, and the mic with you now for start your talk. Thank you.
Thank you very much, and good morning good afternoon to you, and thank you for inviting me for this talk. And if I can share my PowerPoint.
Sure.
And I can start my talk. Share screen. Can you see it?
Yeah, we can see it now. You can start.
Okay.
Okay.
Just get. Well, good afternoon to you. And as you can see, my talk is going to be about organic based visible light communication. And the intention of the talk is just to give a flavor of what this technology is, and really what we have been doing, not what others have been doing. And I leave that for, obviously, for people to find out themselves, although I will give some references to the work which is done by other researchers globally. So why do you need for OLED VLC? And this question is you can always ask regardless of what the topic is. As a researcher, we always need to find out the reasoning why we do research. And this also gives the opportunity to explore our surroundings, just like the videos you just showing about your ancient history of your country. In order to understand it, you need to search. To search, you need to put time and effort and look around and so on. This is the same thing in science and engineering. So we need to identify underlying reasons why this technology is required. Well, the reasons are, of course, it is coming from the domain of communications, communication systems or technology or telecommunication infrastructure without people and devices and so on is almost meaningless. So we have various applications that where the concept of telecommunication is applied. And these are some of the applications that we are familiar, some of them are futuristic, and so on. So you can add to this list as much as possible. And as the world is also getting much more smarter in a sort of global term, then the consequences of these developments in our domain is very severe. And it is this consequences which is pushing the researcher to look for different things. So if we summarize is that more devices mean more data. More data means we must have an adequate channel in order to shift this data from A to B at a global level. And that is where the problem starts. So therefore, we can see the reasoning why one could do research in this sort of area to address this problem of bandwidth. And then we have to understand it within a framework of theoretical tool that we have, and it's been developed over the last 120 years or so. And the famous one is the Martin Coopers, who is a Swedish scientist, who was predicting that, you know, the voice video connection can double every 2.5 years. And if you look at the trend, you can see that it is an exponential increase with the data rate against the year. And this is the one which we were saying that the devices would generate. So if you have a telecommunication network, it's going to deal with this sort of things. How do we measure its throughput? It is three key parameters. One is the cell density, how much bandwidth spectrum we have, and how effectively do we use that spectrum. So these are the three fundamental concepts that we could play with in order to increase the throughput. And these are really the driving force behind the growth of modern telecommunication network. So what do we have, or what have our RF colleagues have been doing over the last 2 or 3 decades? They have not been standing still. They have been doing wonderful research, looking for innovative ways of overcoming this spectral congestion, or the bottleneck that we talk about. And you can see that they have been using the cell density. In other words, they are playing the first parameter, that Martin's equation. In other words, the cells becoming much smaller and smaller and compact. And of course, that is very true. You can increase the capacity by splitting the cell, but at the cost of very, very complex infrastructure, because you will have many base stations and you need to manage them. And then at the same time, as the base station numbers are going up, your channel or inter-cell interference and adjacent cell interference will go, and therefore your signal to noise ratio will drop. So the world of telecommunication, just like anything, is a world of compromise. You add something, you have to give away something else. And then RF has been very good in pushing the frequencies to higher and higher, moving up the frequency scale. And of course, that's a very logical way of doing it, because we know by definition that roughly between 10 to 15% of your carrier frequency is your bandwidth. So it's inevitable that you have to push to higher carrier frequency, which will push you into the millimeter wave range. And then beyond that, you can see what we are going to see. And then a higher spectral efficiency. In other words, how effectively can we utilize what we have by manipulating the signal in time and frequency domain of poles. And that is our creativity. That we are basically compressing a lot of information in a very limited resources. And that's very, very clever. The latter one is this, which is the share of resources, is basically, we are not doing anything much there. We are just using whatever is available out there. It's possible that if someone is not using the resources, then I could use it, and so on. And of course, on top of that, you have the signal processing, which is catering for modulation scheme and coding, and especially this modulation scheme based on the multi-level, stack them up as much as possible, or use many carriers as much as possible, bring the carriers as close as possible to one another, watching out the inter-carrier interference and so on. Or just be brave and go into parallel communication. In other words, you can lay more cable, you can have more antennas, just like massive MIMO, or you can have more fibers if you wanted to. In fact, that is maybe the best option if you want to achieve high capacity communication systems. We have this trend, which is at least last 40 years or so. We have been dealing with cellular system, which moved away from a single transmitter or single base station in a single cell into the first generation, and then into third generation, fourth generation, and now we are fifth generation, and beyond that, and possibly in the next 5 or 6 years, we will be talking about 6 generations. And as you follow this generation, something interesting is happening in this generation. So up to here, if we, up to there, everything is based on RF technology. There was no room for anything else. So if you wanted to bring in any other technology here, they wouldn't listen to you. That is RF, and we will stick to that. However, things have changed with 5G. The 5G says that we need to look at the multiple technology. And the multiple technology is starting with a MIMO, massive MIMO. This is the most important part. And if you can implement massive MIMO, then we can look at it. What are the possibilities in terms of technology that one could have the massive MIMO? To implement the massive MIMO in the RF domain, well, the technology is based around the millimeter wave and possibly terahertz. So these are very high frequency short wavelengths. And then you can ask the questions that how massive a MIMO can be if you are going to use millimeter wave? Or is there a limit for the massive MIMO within the RF domain? And you will find that actually there are. Maybe you're talking about 100 antenna. Then it says that if I'm going to use a massive MIMO using very dedicated antenna, highly focused beam, which we call a millimeter wave, is there another technology which gives you exactly the same thing, but even higher orders of MIMO? And of course, that's where the light comes in. The light, you can have hundreds of lights within a small area, and that is already your massive MIMO transmitter. So the 5G and 6G are talking about a technology which caters comprehensive multimedia-based services, but using different wireless technology. Where that's still is open for questions. And then 5G talks about, uplink and downlink of up to 10 gig that we have not seen it before. It also talks about security. This is another important bit that we need, and then low latency that we need to achieve. And when you look at these three parameters, so which technology, wireless technology, does actually offers me more than the RF does? And this is where we start seeing light at the end of the tunnel, and therefore the concept of wireless optical communication. Throw away the RF as much as possible, then bring in the light as a carrier signal in order to address some of these things that 5G and possibly 6G will be talking in the next few years. So that is the underlying reason why we are basically doing research in the field of optical wireless communication, and therefore using the visible band, and we call it visible light communication or Li-Fi, in contrast to light. So this is my content of my talk. So I'm going to basically introduce this, give some data, and then find out. The concept of VLC is a very simple concept. Everyone has got a light in their room or in the office or in the hall and so on. The lightings are all connected by our backbone power lines. So we already have the networks in the building anyway. This is our power line. And all we need is that these lights, we need to ensure that they're based on LED or laser. It doesn't really matter. And as long as I have my optical antenna, which is sitting here, then I can have an optical antenna on the other side, which is my receiver. Then I should be able to establish a link between the optical antenna at the transmitter and an optical antenna at the receiver. I can also use this power line in order to carry the data. So I could combine the power line communication with optical wireless communication. And I can deliver it already in the building. I don't need to do any wiring because it's already, wiring is there. So that's the concept. So it's almost the same as RF communication, except your antennas are optical antennas. And of course, that once you shift from RF to optical, there are fundamental differences that you have to consider. We know that in an electrical domain, the power is proportional to current squared. In optic, power is proportional to current. In electrical system, the signal can be bipolar, and optic signal can be only unipolar. In optics, in electrical or RF, your antenna size is much less than your wavelengths. In optics, your antenna size are orders of magnitude greater than. And they have significance in telecommunication, these fundamental physical phenomena. And because they have significance in communication, we need to exploit them as much as possible. For example, I leave it to you to think about it. What is the significance that if you have got an antenna which is orders of magnitude greater than your wavelengths of your carrier signal? What does it offer if the wavelengths, if this antenna size is less than the wavelength? Just have a think about it. Maybe we can talk about it at the end. So what does it offer? These are some of the features of it. Of course, you can use LED or laser, just like this light here. High data rate, high security. This is critical, especially in a lot of applications where RF is not welcome. There are many of them. It's a green technology. The green in this case is that it must address the global warming of the CO2 emission. And therefore the green is, it must use less energy compared to RF. That's why it is green. Of course, it's eye safe. It doesn't affect the eye. Ubiquitous, you can connect it in whatever configuration you want. And interesting is that it is not affected by RF-induced electromagnetic interference, because your carriers are photons which are neutral. And therefore, you can operate them in a very RF noisy domain, and still you have a very good signal transmission. And of course, you can make them compatible with the optical fiber communication, which is almost 60 years old. This has dominated the global backbone communication. Whereas this technology is not for a backbone, it is for the last meter front haul of access network. But you can make it compatible in terms of data rate and performance compared to your backbone. So what sort of happening in terms of the light itself? I mean, the light, you can see that this is just a schematic of light evolution taken from the sun and a various light source. That currently we don't use this anymore. We're using this, which is in Kazakhstan. And this is the one which is basically now replacing, which is the LED or semiconductor-based devices. And you can see the power of these LEDs, what you can generate. You can imagine these as your antenna. And this is something we have never seen before. If you look at here, how many antennas you have inside this little area? Maybe 20. Can you put 20 RF antenna in that small place? Not possible. So these are some of the features of it, just to compare and contrast. These are standard lightings that you have. And these are the fluorescent LED, and these are OLED, which are the organic-based devices. So you can see that the organic-based devices are trying to catch up with the standard LED in terms of luminance and so on, and number of hours and so on. But there are other features of this OLED, which is of interest to many people, including us. That we need to do. So if you take these two, which are different light source, these are semiconductor light source, and compare these two, the main difference is this switching here. In other words, for the first time in our lighting history, we have a light source that we are able to switch at very high frequency. Before, with fluorescent and cancer, you could have done it at very low frequency. But now this semiconductor devices allow you to be turned on and off at very high speed. And this is the breakaway between this light source and the one on the left-hand side. So what can we do with this switching? This is what we can do. Of course, if we have a light, we must get illumination because we want to see. On top of illumination, you get data communication. On top of that, you get sensing. And on top of that, you get optical GPS. So therefore, you have one light source with 4 functionalities. Now you compare this with RF antenna and see how many functionality RF antenna has. It's a 1 functionality. This device has got 4 functionalities. So what light sources we have, you can see that we go from standard OLED to RGB laser, micro LEDs, and so on. And depending on their material, the bandwidth, you can see that is linearly going up. That's the good news for us. So, however, we are really interested on this that we want to talk about, which has got a lower capacity, and we'll talk a bit more what does that really mean. So the organic in organic devices, which is LED and laser, which is made up mainly gallium nitride. They give you high power and large bandwidth. 2 key parameters that you require in data communication. And you can do whatever you want with these light sources and so on. This is well studied in the literature. Go and look at this. References 1 and 4 and references within, and you find huge amount of information. What about organic LEDs? Which is, that's how they look like, transparent, thin, you can paint things and so on. And look at this global market. 2019, almost 32 billion. And it is expected in the next 7 years to go up to 203 billion US dollars, which is a phenomenal market. So therefore, for companies to get involved with it and convert it into optical antenna, there is a good incentive as far as the cost is concerned. So 2011, we were the first group in the world where for the first time we demonstrated OLED-based optical communication. And that was the beginning of VLC with OLED. This is how it looks like. It's a layer structure. I don't want to go through that. I'm not a material scientist and so on. So you have anode, cathode, and there you have got various materials in order to generate electron hole, and therefore you get photons and so on. But let's look at the features. You know, very thin, 100 to 500 nanometers, made of long chain of polymers. It gives a better resolution, better image quality, mechanically very flexible, and so on and so on. And they last over much longer lifetime. And this is the beauty of it. How you can create light source depending on your need. And then you can use the same light source as your antenna. That's why I guess they are. Some applications. You can see that the modern cars, the bicycles, a motorbike, and so on. So you can actually now, you can make whatever you wish to out of these devices. Okay, let's look at some of the application of it. So this looks like the customer needs, this customer type, and I don't want to go through that. You can see it for yourself. Already, it is really moving the areas that we couldn't even imagine. Look at these clothes. These are not reflective. These are actually a light source. So imagine that this light source that these firemen are wearing it, not only is giving you illumination, but it's also sending key data, safety-related data to the control module or command and control center. So the light within the clothes of these guys is acting as transmitter. And that is why it is so wonderful. So if that is the case in here, then you can say that if I have a organic LED in the car as well, therefore these lights can also send information. If I'm using it as a glasses, they can also act as a transmitter or a receiver and so on. Then you can apply that logic all the way across the application range. And these are some of the looks at the data rate and various technology in terms of modulation schemes, modulation equalizations, pre-equalization, post-equalization. It just says how many papers in the last few years has been published in this area. We were one of the groups that the first one globally that we demonstrated up to 10 meg of OLED-based visible light communication using wavelength division multiplexing and some equalizations and so on. However, this data rate is low compared to standard inorganic LEDs. There are reasons. Reason is mainly physics and materials. And if we can improve the physics and materials, and therefore these devices can turn on and off at much faster rate. If that happens, this data rate that will, by definition, must go up. And I will show you some slides later on. So if we have these devices, what do we do with it first? Of course, if you are new into this area, the first thing you need is to characterize your antennas. So you will have a, let's say you have OLED transmitter and you can have an OLED photodetector. These are the standard tools you will need for characterization of your device. Of course, as a light source, then we can look at its light profile. Then we look at the light responsivity and photodetector responsivity and so on. So we are going to use some of the characteristics of the OLED and show you some plots in terms of its optical and electrical features and see that what they are. Well, we are electrical engineer. The first thing we do is always model the device. So we have a layered semiconductor structure. So it is sandwich type, so we can always represent it as a very simple RC filter. And that's it. Simple RC filter represent your OLED. Once we have a model of it, then we can find out what's the cutoff frequency, and the cutoff frequency is a function of the capacitance, and the capacitance is the bottom. Then we can do some measurements, look at the power versus the current, which is goes through the device, and see that, okay, optical power versus current is almost linear. And it's quite linear over a much very wide range of drive current, which is exactly what we want, because linearity is very important for us in some applications. We also done that, look at the bandwidth against frequency, because okay, we can measure, for example, 3 dB bandwidth, depending on what bias voltage we have. If you reduce the bias voltage, your 3 dB bandwidth will drop. So this is essential that we must understand this before we do anything. So the low bandwidth, as you can see from here, is mainly dominated by RC time constant, which is this one here. And also the size of the photodetector, how big it is, and so on, which is fundamental. We have seen it in our second-year degree courses in electrical and electronic engineering. And these are some of the OLEDs that we have been recently looking at. These are different OLEDs, different shape, and also we have a curved OLED, which we have not seen it before. But so we have taken this and look at the beam profile. Our ideal beam profile is over Lambertian. That's a crystal ball. We want to know which one of these are actually close to the crystal ball. And you can see that they're almost roughly there with plus or minus a few degrees. But if you narrow the angle, they're almost the same. Very close to the Lambertian of order 1. So they behave almost like any other light source that we have seen before. They're not very strange. If you want to read more, look at this paper that we published recently, and then you can get some more information. Then we were interested is that, okay, we looked at the flat one. What about if we bend it? So this is our light source. Now the light source, you can see that it's bending with certain degrees. What we are interested in, whether when you bend the light source, the bandwidth will stay the same, or it will change with the curvature. And also the beam profile will be uniform across here, or it will also change. So we did that, and students did some analysis. We come up with a model for it and so on. And you can see that model has been written here. So we use the model to see that whether it matches with our measured results. So what do we get? We get, look at the normalized intensity. And this is our curved one, which we were talking about. And these are all flat. So D5 is the curved one. You can see that they're almost the same. So it means the beam profile doesn't change much if you bend it. Of course, if you bend it beyond a certain point, it will just break. So it looks like that if I put this around the columns, I will get a uniform light distribution, which means my signal to noise ratio at the source will stay almost constant. And that's the good news for us. Because if it otherwise, if it changes with bend, it means that I have got to put maybe more current around here than at the center. And so, and that is something that is very useful. Then we compared it with the standard. This is a standard inorganic LED, which is based on RGB, red, green, blue LED, which you can see that this is red, green, blue LED. And this is the organic LED, which is this one. And you can see that the peak is almost around the blue. And then second peak is like green, very little red. This is the one we tested. You can pick up another OLED. It may have slightly different composition of RGB. But what it's telling us is that it is almost the same with two peaks around blue and green. And then obviously there is no separation between green and red. It's almost like a single band between just those two primary colors. So it is, again, you can conclude that you can treat it as the same as RGB LED. Then we took the curve OLEDs, and as you can see here, this is a curve OLED. Then we said, okay, let's look at this bandwidth characteristics. So we built the circuit, and then we did some measurements, and these are various bandwidths that we have seen. Although they are very low, it doesn't matter. And you can see that the bandwidth changes with the current as expected, and so on. So what we wanted is that, okay, these devices, if you can bend it up to a certain point, the bandwidth doesn't change, it's very stable. And that's exactly what we were looking for. Then an antenna, which is very stable, regardless of how much you curve the surface of your antenna. Then we looked at the temperature profile, because LED and OLEDs are very cool devices. If you, for example, take a fluorescent light or incandescent light, try to touch it after a couple of hours, it will burn your hand. These devices are very cool. You can touch them. There's absolutely, no heat. So they are very cool and so on. So look at the distribution. This was for device 2, and you can see that really the temperature doesn't change at all. That's why they are very energy efficient, because they don't convert the energy into heat, they convert the energy into illumination or luminance level. And that's why they are 80% energy efficient compared to 37% fluorescent light and only 5 to 10% incandescent light. Now, there is a fundamental question that we need to ask. How low modulation bandwidth compared with an organic LED? Very low. And is this sufficient for real application? Because immediately a lot of people will say, oh, the modulation is very low. What can you do? You cannot do anything with it. I think that's a very wrong way of looking at the concept of communication. Communication doesn't always mean transmitting at hundreds of megabits or tens of gigabits. No. Communication is like RF spectrum, it's a range. Depending what you want to do, you design your system. So the communication could be defined as a high speed, which is here, anything up to a few gigabits per second, and low speed could be from a couple of hundreds of hertz into lower megahertz. And that's perfectly okay. And if you look at, we are not interested in this at this stage. We are interested in this. And if you look at that, this can be split into IoT-based devices, in other words, device-to-device communication, which is part of the smart environment. Or it can be for localization, your optical GPS. Or it can be for pure device-to-device communication. So these, you don't need high speed. It's not necessary to have a high speed for that. It's overkill. It's like buying a Rolls Royce and trying to run it as a taxi. To charge exactly the same one, I was just using standard, Skoda car. Doesn't make sense. These, even lower, these are just sending some location information and so on. So the question is that for this sort of application, why do I need high-speed data communication? It's like using millimeter wave for a lot of low-frequency communication. It just doesn't make sense. So we need to get used to this concept that data communication doesn't always mean multi-gigabit communication. So therefore, don't get immediately say that, how fast can it go? Tell us that, what is its use? Where can I use it? Depending on the need for the data and so on. So in terms of the VLC system, we have uplinks and of course downlink. Uplink is from my light sources coming down to my device, and I can use both of them, organic, inorganic, or organic. And I can also use the same thing for uplink. I can use visible band, or I can use infrared band. Of course, uplink by definition is much lower speed than downlink, because most of the time we are receiving information. So they can operate that, they don't have to be symmetrical in terms of speed. They can be asymmetrical. Or you can mix it with Wi-Fi if you wish to. You can have your download Wi-Fi and then uplink Wi-Fi if you want to do that. Then we put this device into a proper system. This is a all organic VLC system where we have our organic LED and organic photodetector. That's organic photodetector and organic LEDs. Rest of it is almost the same as a VLC. And the other side is that we are just doing some equalization, but we are using machine learning, which is artificial intelligence, in order to compensate for dispersion. So we can push the bandwidth at higher. And if you look at here that we have a bit error rate versus the bit rate, and then we have plotted the forward error correction limit, which is a standard bit error rate limit of roughly 10⁻⁻3. And if we choose this, you can see that we can achieve up to 440 kilobits of data using 135 kilohertz bandwidth. Yeah, we are almost 3 times its own bandwidth. We are generating data or transmitting data using this particular setup, 3 times its raw bandwidth, which is fantastic for a lot of application where you're sending short messages, like in medical application, like intelligent transportation, like manufacturing, like agriculture, so where you don't need a lot of data rate, large data rate and so on. And then you can push them up if you want up to 1.1 megabits per second. If you lower your standard bit error rate from 10⁻⁻3 to 10⁻⁻5, then sorry. And so therefore you can, almost increase your bandwidth by 2.5 times to 1.1 megabits. And then we moved on, okay, we have organic devices. Can we make a MIMO out of it? Why not? I mean, what is MIMO? MIMO is a multiple transmitter and multiple receiver. And this is the system we built in the lab, multiple transmitter, multiple receivers. And then use the on-off king standard intensity modulation schemes. And you can see that we have a very good I and a very low Q. And we are meeting a bit error rate of 10⁻⁻6, which is much lower than the 10⁻⁻3. So again, for MIMO application, fantastic. Then we looked at can we apply OFDM, because OFDM is part of the LTE, 4G, 5G. A lot of people are doing research on OFDM. It says, can we use this OFDM in live? Yes, of course. And then we compared this with standard on-off keying, and we applied equalization, again using standard equalizer and neural network-based equalizer, and so on. And again, you can see that for OFDM, this is almost the same as RF, except that optical part is different. And then again, if you choose a 10 to the power minus 3 as our reference level, you can see that our constellation diagram, the eye diagrams are well below that, and therefore it also demonstrates that OFDM it can be used, and a lot of people have been using OFDM. Although my own personal view is that I don't think you really actually need OFDM in VLC. You can just do it on-off keying. That is as good as OFDM. But if you need fancy things, then by all means go and use OFDM. Okay, and then we push the data rate to 20 meg or 20 megabits per second. And again, we use the on-off keying. We used equalizer, which is based on a neural network. And then our device had a bandwidth of 350 kilohertz. So you can see that from 350 kilohertz, we delivered 20 megabits per second. And you can see here, depending on the size of your neuron, you can improve your data rate. So again, that is processing complexity will give you the data you want. What else do we have? And then we push these things to 50 megabits per second. And this time we use the wavelength division multiplexing. So we have three wavelengths. Combine the different colors, each carrying its own data. And then we manage in total to achieve 50 megabits per second. And this was in 2015, almost 5 years ago. So you can see that using wavelength division multiplexing and without equalization, then you can achieve very high data rate using these devices. And then beyond 50 megabits per second, then this was another system that we built. Again, this was using the ANN equalizer. And you can see that for the bit rates, we are basically pushing beyond, for example, this in terms of LM, we can get signal technology of 20 dB, meeting our FEC limit. And of course, if you move away and adopt other things, then you have to pay a penalty. But the interesting is that you're achieving speeds of more than 50 megabits per second. And again, if you want to look at this, please go to this 2019 paper, which was published, then you can get more information. And then we tried a multi-carrier modulation scheme, which is almost the same as OFDM. However, we removed all the IFD and FFT. So basically, we had a bank of filters at the transmitter, and then another set of filters, or demodulation, which is very similar to QAM at the receiver, and that's known as a multi-carrier phase modulation without FFT and IFT. It's very efficient way of driving. And this one was for the curved LED that we are interested in. You can see the antenna here. So then we compared the flat antenna there. We just wanted to know that whether there will be any differences, major differences between these two. And there we are. So we did for the flat OLED. These are various flat OLED depending on the size and so on. So you can see the D2, which is smaller, gives you the better performance. Very nice constellation diagram. And then we compared it with flexible OLED. And you can see that again, flexible OLED gives you the bit rate well below the boundary of your FEC limit. And just demonstrate that again, your SNR is not changing that much if you bend your device. Then we did further work for the OLED and see that whether there are any symmetrical pattern with respect to the center of the beam. And says, of course, there will be. So you can see that. And we are, again, if you take this as your limit, you can see that provided you operate here, then you will meet the standards for both curved and OLED and flat OLED. Okay, of course, flat OLED will give you slightly better because slightly more uniform power distribution. And then we said that, okay, what about if you apply this in the shopping centers and so on, and the big places? What will be the scenario? So we developed a model that we can now start modeling any scenario you want for indoor environment, and we can simulate it. And then once we have got the simulation, then we can go away and build the real scenario. So these are some of the simulations that you can see that you can build any room, any indoor environment, and then you can use flat or curved OLED. Okay, for example, we put here around this column curved OLED around here, or we can put a flat OLED and so on. So we create this in the software, and then we look at the line of sight, non-line of sight, the combination of those two as the light leaves the transmitter and receives at the receiver, and see what the scenarios are. Okay, you can see that. So looking at the optical power losses for empty room, furnished room, and so on, look at the impulse response, and therefore the delay spread. The delay spread tells me that how much spreading you have, and therefore what will be the maximum data rate I can transmit. So the lower the delay spread, the higher the data rate will be. So you can do these sort of things using MATLAB if you wanted to. And then we do the bit error rate measurements for the shopping centers. And you can see that again, we are interested in these regions here, and most of them are meeting that bit error rate limit of FEC and so on. Of course, things will change with distance because your power budget is disturbed because your receive powers get lower and lower, and that applies to any communication system. Okay, and these are all line of sight. There's no reflections at all. And then we did three-dimensional simulations of environment, and again using curved systems, and you are interested against what will happen. Again, we looked at the beam profile and so on, and you can see that curved and flats are again almost the same, whereas in this case, the curved flat is much more focused around the very smaller angle, which is expected anyway. And then we looked at the offices and did the measurements against for the bit error rate for the flat and curved OLED. And again, you can see performance as long as they meet the FEC limit, and each of them has got its own feature. Remember, the curved OLED will have a symmetrical distribution around the center of it, which is basically shown in here as well. So, you can use them into the office, and we demonstrated up to 4 megabits and 6 megabits of data. And then we looked at we are looking at open corridors and semi-open corridors and so on. So these are large areas, and therefore you get a lot of reflections from there. And we said that we want to know what is happening, and there we are. So we looked at two of the cases and looked at the power penalty in here, and then look at the RMS delay spread. And we see almost the same pattern as a smaller room, but in the numbers are different because it's a much larger. So it means if they are used as a display panel or illumination panel, they can also be used as an optical transmitter, provided that you understand the power losses and then delay spread. And then we moved a step forward because the current system OLEDs are on up to 350 kilohertz low bandwidth. Then we had a big project with UCL in London, and we built a new OLEDs, and we tested that, and these OLED basically increased raw bandwidth by 3 times. So therefore we had, these are the OLEDs that we were designed at UCL, tiny OLEDs. But what we achieved was that the bandwidth was almost 3 times, reaching almost 1 mega of raw bandwidth. So if the bandwidth is increased by 3 times, your data can be increased 3 times, means that you can transmit up to 200 megahertz of data using 1 megahertz of bandwidth. Okay. Test on these devices to characterize them, find out about their stability, and so on, which are published in the literature anyway. And we put into system. So these are the OLEDs designed in UCL. So we brought it to our lab. So we have transmitters and receivers, and then we developed the VLC systems, and we did all the standard tests and the measurements. And again, we demonstrate that the system works beautifully within the FEC limits up to the bandwidth that we are interested. And then we put into the MIMO case with the CAP. You can see that, again, the new OLEDs are constellation diagram are absolutely perfect, and they are well within the FEC limit, and therefore they are fantastic antennas. So in other words, I've got a few slides and I'll finish. Okay. So the question is that how do we keep continually increasing the bandwidth of these OLED devices? Or how do we increase the bandwidth of VLC things? One solution is that try to exploit the near infrared transmission window. In other words, go beyond the 700 nanometers, so 700 to 1,000 nanometers. And this is the area that people are now started working on it. So in other words, it looks like that we have the visible band, no gap, all the way to upper infrared. In other words, you can push it all the way to 1550, 1600, or maybe 2 nanometers range. So that is the new devices which are coming up in near infrared transmission. And that way you will have a massive, massive spectrum. And OLED devices, they have features that this near infrared is, which is better than the visible range in terms of the mechanical things and the way they are deposited and fabricated. If you want, there is a paper just published in April by colleagues from UCL. Go there and have a look at it. So what have we, this is my conclusion. It says that this slide is future. This slide will replace a lot of lighting in indoor environments, especially in big places. And since we know that any lighting which is based on semiconductor devices can be used to transmit data, and since we can have detectors based on this, and therefore they can be used as the receiving. So we need to watch out for these OLED and therefore exploit their full potential. Of course, we need our material and devices guys to push their devices to their limit to have a faster and faster rise and fall time. So we can basically achieve even at 1 gigabit per second, and that will be the ultimate goal. This OLED compared to standard LEDs, they are linear. Their power current characteristics is very linear, wide dynamic range, and that is wonderful for multi-carrier modulation scheme like OFDM. Because OFDM is very sensitive to the linearity of antenna. So if you can make that linear and wide dynamic range, it means you can have a very high peak to average power ratio in OFDM. That's exactly what you should have. At the moment, compared to standard non-organic, inorganic devices, they are still high cost. But manufacturers are, of course, all the time working on it and so on. It's possible in the next few years, they'll be at the same price as the standard LED that you want. So do show an interest and get some of these and take it to the lab and do basic stuff with it. Yes, don't push for the high data rate. Try to send things at a few kilo or even megabits per second, and then get the concept down and see whether using that low bandwidth, how much information you can pump into it to go to around 200 megahertz if you can. Okay, so this is my acknowledgement, especially for Tawfiq and Dr. Maiden for the invitation and for being in touch on a regular basis to make sure that this event takes place, another one will be online and so on, which I'm very grateful. And if you want to read, these are the books that we have written, then you can go there and find out as much as information. And that is it. If you have any question, I'm more than happy to answer.
Okay. Well, we would like to thank Professor Fary for wonderful talk. I'm really was enjoyed for the great information and received from you. Also, I read your last version of your book. It has helped my students so much. So thanks, Dr. Fary, for this book. Now we will. Thank you. We can receive a few questions. We have around 5 minutes. So we can receive question from the audience.
Sure.
Okay. First question is talk about the competence between millimeter wave and optical wireless communication, either for indoor and outdoor communication.
What is it, sorry?
The competence between millimeter wave and optical wireless communication.
The confidence. What does that mean, confidence?
Competitions. There is
some competition, sorry. I mean, there is, I don't think we should look at, we should never, we are a scientist, we are an engineer, we shouldn't even use these words of competition, yes? Because as far as I'm concerned, I'm not competing with anyone.
Yeah.
I am looking at one part of the electromagnetic spectrum. My colleagues are looking at other part of the electromagnetic spectrum. And then we are together, collectively, we sit together in standard bodies and then decide which one of these technologies is best suitable for which application. So the question, the right question is that, can I use these two technologies 100% in all applications, or do they cater for different applications?
Yeah, yeah,
I think
right.
If we take it this way, I think in some areas, definitely millimeter wave must be used. Okay. In some application, I think it will be the VLC that must be used. For example, if I'm in my room here and my lightings are LED, why do I need a Wi-Fi here? It just doesn't make sense. I can use my lighting as part of the telecommunication infrastructure. Why do I need to put another antenna and so on? If there are areas that were, if like underground, tunnels, and places like this where you cannot take the antenna on RF, what do you use? You can use light. Or if you go to the hospital, you cannot use RF. What do you need to use? Then you can use light. So this is how they are not competing, they are complementing one another.
Complementing, yeah, that's right.
Yeah, that's the best word. We are complementing. If you use competition, means that I don't want to compete with anyone because this is a science, yes, but I want to complement as much as possible.
Yeah, that's right. I'm just read the question as it was written, so I just transfer the question.
Sure. This was on the questionnaire, yes.
Yeah. Another question: is there any limitation when using optical OFDM or MIMO on organic LED? Any limitation over organic LED when you use OFDM or MIMO, or similar to VLC?
No, I think the limitation is the size of the devices that you have. Don't forget that the LED lights, by definition, they are MIMO anyway, because they are made of different type of RGB devices.
Yeah.
So you already have that. Okay, once you get bigger, it's about manipulation of it. Yes, so it means the future organic or inorganic based LED should have a bit of electronic inside it. So you can open it up and you can tap into it. Then you can each individually, either a single LED or a collection of LEDs, you can reconfigure. At the moment, you don't have that access because it comes as one device, sealed. But if the future LEDs that you can play with it, which, because it's a grid, it's a LED, it's arrays of LEDs. So it means that limitation is that manufacturing. If a manufacturer will allow me to have access to the grid, then row and columns, then I can do whatever I want. That will come. Future LEDs will be like this anyway.
Okay. Due to that the time was limited, so it's an tight time. So we would like to thank again Dr. Fary for his answering and presentation, and thanks for attending the conference for as invited speaker. And I learned more from Dr. Fary during his collaboration together. And thanks, Dr. Fary, for your time. And we are sorry this is a holiday in UK, but we also in Egypt. But we thank you for this.
It's a pleasure. I wish you a very good conference, and I hope that it goes well.
Thank you.
Thank you. Thanks, Professor Fary. Okay.
Thank you.
Okay, Dr. Tawfiq, could you announce for the parallel sessions that is running after this session? We have 4 parallel sessions.
We are now we're closing this presentation, and we will start the sessions after 1 minute. So be ready to start the sessions in parallel sessions according to the schedule. Thank you.
Thank you so much. Thanks.
Thank you.